today. So it's just one of the joys of technology. Right, here goes. You should be looking at the white piece of paper with my writing. Agreed? Yeah. And when I move my fingers, are they moving, or does it feel like it is shuttered? Okay, at least one problem is fixed, which is the Zoom not working. So what we're going to be doing today is hypothesis testing on the difference between two samples. So it's going to be on the difference between two proportions. I mean, that seems like we've been doing this forever, which we probably have. Hasn't it been single proportion, double proportion, single mean, double mean? We've done sampling distribution with those things. We've done confidence intervals with all four things. We're now going to do hypothesis testing with all four things. And this is the second one of the four. So essentially, if you remember what we did last time, a hypothesis test is a formal way to prove or to try and prove that there's statistical evidence that something is true. We did it with a single proportion, and there were three versions of that. Is there evidence to prove that P has changed and now it's bigger than it used to be, that it's less than it used to be, or it's different in some way from what it used to be? And we went through a whole process of calculating a Z-score, and then that Z-score led to a magic guy called the p-value, and then we just did the test. Is our p-value less than the significance level alpha? And alpha is either 1, 5, or 10%. And if it was, you could say, yep, we have evidence to prove what you thought was true. And if it's not, all you really say is that there's not enough evidence to reject the null hypothesis. Okay, so let's give you a background by picking a story and showing you how hypothesis tests for the difference between two proportions would work. So we are going to do our usual made-up stories because it's easy for me to do that. Let's suppose that you had French, just to be different, and Americans. And we were interested in this particular one that we want to prove that a greater percent of French people, right, voted in their last presidential election than the Americans. So the French have a thing called the presidential election. Their politics are a little bit different from American. So anyway, they have a president and they elect him every, I think it's longer than us, every 5 years. So you collected a sample of 200 Frenchmen and call that N1, and this is P1. And P1 hat is that 70% of them said that they voted. Don't care who you voted for, just that you voted. And they collected a random sample of 400 Americans, people. We'll assume that we are talking about people who are allowed to vote and are old enough to vote. And out of that, we got 65%. Now, so the question that we're interested in is it true to say that French tend to vote more in the presidential election than Americans do? Right, that's essentially what we're trying to do here. So we have to have a significance level for this proof. So in this hypothesis test, do you want 1, 5, or 10? You need to pick it here, so just pick one. You're normally told it in the question. 10. That seems a good answer. So you might think, why 1, 5, and 10? Well, see if I get it wrong, which actually significance level is your percentage you get it wrong. If I use a 10% significance level, I'll be wrong when I say something is significant 10% of the time. But I think if I made a mistake in this, nothing really horrible is going to happen. Would you agree if I was comparing two medications, I'd probably want 1%, right? So if I say the first one's actually better than the second, I'd like it to be true a lot of the time. Like 1% of the time I'm wrong, I guess I can. You have to live with that because nothing is perfect in the real world, right? Nothing is perfect in statistics. You have to, decide on your level that you want to work with. So we're going to have a null and an alternate hypothesis. It's called the null hypothesis. And this is the alternate. The null hypothesis is that they are equal. And that is always going to be the null hypothesis when you're comparing the difference between two proportions. The real value for the French is exactly the same as the Americans. Now, the alternate is what you believe is true and you want to prove that it is, or hope that you can prove that it is. The French, which are 1, is bigger than the 2. Now that becomes P1 greater than P2. Does that seem reasonable? Right. The null hypothesis is that they're both the same. The alternate, the one you're hoping to prove, is that the French P1 is bigger than the Americans P2. But that's actually not the way that it's written in a fair number of textbooks. Somebody trying to join but can't get in right now. That's not always the case. This is the altered version of that same thing. Now, if you think about it mathematically, aren't these two guys here exactly the same as these two guys here? If you're saying they're equal, is it the difference between them 0? And if you're saying the first one's bigger than the second one, would you agree that P1 take away P2 greater than 0 is the same as this? Does that make sense? Now, this version is the most common one that you're going to see. And this is a version that we're going to be using. And it's the one that WebAssign uses. So the process of going through each stage is going to be very similar to the one that we did with the one sample, only we're now going to do it with the difference between two samples. So our test statistic, well, it's going to be P1 hat take away P2 hat. And in this case, 0.7 take away 0.65, 0.05. That's a good start. We're then going to find a thing called the Z-score. And the Z-score has the following formula. Has anybody want to have a guess at what the Z-score might be for this one? If you've never seen it before, it really is a guess, but what do you think it might be? No, nothing.
Would it have to do something with the 10%?
Not yet. That'll come later. Okay. P1 hat take away P2 hat over the standard error of P1 hat take away P2 hat, which if I put in more detail, this one will test your memory. What is the standard error of P1 hat take away P2 hat? if you use it in the context that we've got here?
P1 times PQ divided by N plus P2 minus PQ2 divided by N.
Does that kind of look familiar? It's just another version of the combined thing, right? Agreed. Isn't that the standard error you use when you make confidence intervals, for instance? Right, that's the standard error. So in this particular question, P1 take away P2 hat, we already found him, he's 0.05, so I'll just write that down. All over the square root of P1 hat, 0.7, Q1 hat, what's left, divided by 200 people, plus P2 hat, which is 0.65, there it is, times what's left, 0.35, all divided by 400 people. Now that is one ugly looking calculation, agreed? But you can actually do it, if you're careful, in one go on your calculator. So on this calculator here, I'm going to try and do it. 0.05 divided by square root 0.7 times 0.3 divided by 200, add 0.65 times 0.35 divided by 400, and hit enter, and I get a z-score of 1.24. So far, so good, right? 1.24. Bring this down a touch. I don't know, we're about 2/3 of the way through. We're almost there. I've found the z-score, which is pretty important. I'm now going to get the p-value. And in this case, the p-value is the probability that you get a z-score bigger than or less than 1.24. We have to make up our mind, because if we go one way and not the other, it won't be correct. There is a clue here. It's right over here. Can you see this fella? Well, this one here as well. Can you see it's a greater than? Don't we call them right-tailed tests? Right, it's pointing to the right. Right-tailed test. So right-tailed. And at this point, salt takes over, right? And so I'm going to close this window, open up salt, fingers crossed. Are we looking at salt? Oh, great. So I'll move this up, move this window out the way for a minute. Just make it a little bit bigger, probably too big. Hit salt. Come on. There we go. There. Are you looking at the normal distribution picture? Okay, so the guy we want is a right-tailed test, and Z has to be bigger than 1.24. So right-tailed, go over here and go 1.24. And can you see the p-value? This number here, this decimal here, does it not count as a p-value, right? So our p-value is 0.10, I don't know, 107. That's basically the only bit where you need salt. In the olden days, you just looked it up in a table, or you use your TI-84. There's a way of doing it with that. But we got a p-value of 0.104. Me personally, I like percentages, so I'll call it 10.7%. And to finish then, we do a test. And the test is always the same. And it doesn't matter whether it's a greater than, a less than, or a not equal to. It's the same test every time. And in this test, you just ask this question. Is the p-value less than the significance level alpha? And is 10%, 10.7% less than 10%? And I think the answer is quite obviously no. Agreed? 10.7 is not less than 10. It's a no. That means, unfortunately, then, that we haven't been able to prove what we thought, that the French vote more than the Americans in their presidential election. Because when the answer is no, the jargon sentence is there's not enough evidence to reject H0. That's pretty much all we can say for sure is, well, we haven't been able to prove it, not enough evidence. It might be true, it might not be true, we just don't know. When you look at that entire process, it's very similar, isn't it, to the one proportion one that we did last week, right? It's got this setup, you know, a null hypothesis, an alternate. It's got a different formula, okay, for the z-score, but apart from that, it's still a z-score. And then you have a p-value, which is exactly the same, really. And then a test, which is exactly the same. And your conclusions based on that are the same. So yeah, I would say, you know, a good 90% of the two are very similar. And the big diffy is this one, right? The big difference. You know, the formula is a little bit awkward, but that has to take into account the two, pardon me, the two different groups. Any questions about that process? You feel okay? It's one of those things, if you do enough of them, then you get really good at it. When I was grading your tests, some of you forgot that there's proportion questions and that there's differences in mean questions. And so I guess what happened is that you just did everything like it was a proportion question. And that doesn't work for half of them. So make sure that you understand when it's a proportion, right? Percentage of people who said something. Where the other situation would be the average height is 40. You know, is it bigger than 40? Is it less than 40? And that's quite, it has quite big differences when you do confidence and later on when you do hypothesis testing. Okay, I'm ready to do another question from scratch. I'm going to stop sharing for a second. And I have all of you here. So I'm going to have I don't know what I'm going to do. Oh, let's do something different. We're going to have the over 30s, and that includes 30, and the under 30s. Right? And I'm going to ask you, and you can take part or not. And we're going to cheat. So every single one of you isn't a person. Every single one of you is representing 100 people. Otherwise, my sample size will be too small to make this worthwhile doing, right? But I just want to do something different. So I'm going to think of a question that you would be honest about and wouldn't feel uncomfortable. And I want to see if I can find something that there might be a difference between what a 30-year-old would do or older compared to what an under 30 would do. Any ideas a question we could ask to do that? Say again?
Wash their hands when they go to the bathroom. Actually, that's a weird one. I see a
I
lot
don't
of
know if you want to do that one because people will probably be biased and say yes, even if they don't.
Okay.
But let me tell you, from my perspective, men are not great at it.
No,
If you ever go into a casino toilet, the number of guys who don't do it is surprising. I'm just telling you that right off the bat. Now, I have no idea what happens in female toilets, nor do I want to know, but I can tell you that's what happens in male toilets.
I
It ain't
notice
that good.
always the older people in the female bathrooms at my work that don't wash their hands. Usually the younger people do. It's the older females that don't.
Yeah, I don't want that question just because people will lie because they don't want to say something like that. But it's a good question. Right. Oh God, I'm trying to think. Try to think of something, and if I can't, okay. Here we go. Rock and roll music. Right? How many of the over 30 guys like rock and roll music? Am I the only guy? One? Okay, we got two. So that's P1. Two out of, how many of you are volunteering to tell me you're over 30? And please at least be one more person. Yay. Oh, two people. Great. So 50% of the over 30s like rock and roll music. If you don't know what it is, you don't like it, guys. So you can't vote for it, right? So let's do the under 30s, which is basically everybody else. Okay, under 30s, let's go. Well, Melissa's dancing to some already. How many like it? 1, 2, 3, 4, 5, 6, 7. Okay, that's 7. Out of 1, 2, 3, 4, 5, 10, 15, 20, 29, take away 4, 25. And that comes out as a very respectable difference. 28. And then I'll do the cheat. I'll actually just do the cheat with a factory 10, right? That way we keep the percentages the same, right? So we asked 40 over 30s and, 20 of them liked rock and roll. And
Will
we
you
went,
share your screen again?
oh, yes, that would be helpful. So we asked the over 30s and 50%, which I'm now calling 20 out of 40, liked it. The under 30s, 70 out of everybody else, that was 28%. So based on that, wouldn't our assumption probably be the over 30s like it more than the under 30s, right? So let's set up our null and alternate hypothesis. And the null hypothesis is, okay, this is 1 and this is 2. So P1 represents M, P2 represents M. The null would be that they are equal, right? But you will write that down like that. And the alternate is that over 30s like it more than the unders, but we will write it down like that. So that's the one we'll use. So far, so good? I got a window problem. Hold on there, guys. Everything's reacting very slowly today. Very strange. Right, let me stop this window for a second. Oh, flipping bananas. Okay. Okay, I've lost me thing. Can you still see me, guys? Right, so now I have to figure out where that window is hiding. Come on, window. I know you're there. You're not over there.
If you're using a Windows computer, hold Alt and then press Tab once
Okay.
while holding Alt. And it will show a list of all of your open windows, and you can click on one or keep pushing Tab until it's highlighted it.
I like that. Okay. And I found it. Thank you.
You're welcome.
You all got that? Alternate tab. You probably all knew that. I just didn't. There we go. There. Paper, writing, good to go. We still got a little bit to do kind of at the front end, and then we'll do the hypothesis test. So here goes. First thing I'm going to do is decide on a significance level. What do you want? 10%, 5%, 1%?
5.
Go for 5. Sounds like a little bit different, right? Right, we've got this fella set up. I should be able to do the z-score, right? Which is P1 hat, take away P2 hat over the standard error formula, which is this ugly guy. And in this case, 0.5, take away 0.28. And this is going to be 0.5, 0.5 over 40, a 0.28, 0.72, and that's over 250. And if I'm going to do this guy on a calculator, I'll need to put a bracket around that. Doesn't seem very important, but it is. Why do I need to put a bracket around that top calculation if I want to do the whole thing in one go?
Because they'll divide before subtract.
Yeah. And you'll get a weird answer that's not the right answer. So it's to do with ordinary operation. So I'll put a bracket around it, just to be safe. 0.5, take away 0.28, close the brackets. Now I can divide. Big square root. 0.5 times 0.5 divided by 40 plus 0.28 times 0.72 divided by 250. And it looks like 2.61. Why do I feel confident I am going to get a significant result in this hypothesis test, even although I'm only about halfway through, a little bit more than halfway through?
Because you have such a high z-score.
Yeah. Now, if that z-score had been bigger than 3, I'd bet my money on it that I was going to get a significant result. But 2.6 is pretty decent, isn't it? It's a pretty high number. Probably going to make it, right? That's my gut feeling. So we shall continue and find out. So what we now have to calculate is the p-value. So that's going to be the probability that you get a z-score. Oh, darn it, I should have done a less than, but you know, you get what you get. Right, so would you agree that's another right tail test? I think the next question I'll do will be a left-tailed, and then the one after that I'll do is a not equal to test, right? So we get a shot at all of them. So that's where Salt takes over, right? So I'm going to stop sharing this one and start sharing my Salt screen. That look good? See Salt? Okay, so it's still right-tailed, so all I need to do is change this to the new number. The new number is 2.61. And right underneath it is 0.00453.
Professor Robertson?
Yes.
Yeah. For the calculation, I got a negative number. Does that matter? And then
Did you do P1 take away P2? And it sounds like you might have got these the other way around, or you didn't put the brackets in.
okay,
So there's one or two ways that might have gone wrong.
okay.
Right, the guy I've got here is 0045. I'm going to return now, and you can check on my calculator that you've done exactly the same thing. And you might notice what you didn't do quite exactly right. Okay, so put a bracket, 0.5 take away 0.28, that is positive. Square roots are always positive, so this answer is guaranteed to be positive. So I'm pretty comfortable that the 2.618 or 2. Actually, now I think about it, it's closer to 2.62, isn't it? I'm assuming that's not going to make a heck of a difference. That ends up being nothing 0.45%. So working now, Nikia?
I'm still putting it in. Okay, yeah, I got it.
Yeah.
It was the
So,
bracket. Thank you.
Yeah, easy done. It's hard to tell that you've done it wrong because the number you get very often looks quite plausible, right? And so you're never 100% sure that it's wrong, but if you're
Yeah.
careful, you'll be fine. Right, we've got a p-value. We're ready for the test then. And the question is our p-value less than our significance level alpha? Is 0.45% less than 5%? The answer is yes. Which means that we have actually proved something, right? There is enough evidence to prove that the alternate hypothesis, which is basically this one, right, is true. So we can say with a fair degree of comfort that, yeah, over 30s like rock and roll more than under 30s. That seems as a reasonable conclusion to make. Any questions about that one? Okay, so it's basically just going through the same process with a different story. So this next story, I'm going to look for something, I'll just make one up, where we are trying to find P1 less than P2, right? Because both the stories have been the first thing is bigger than the second. Let's do a story where the first thing is hopefully less than the second, right? So we went and we collected data on 2 groups, and we will have we'll have Seahawks fans, they'll be group 1, and Sounder fans, that's group 2. And we asked both of them the same question. And the question we went and asked them is, what would we ask them? Do you think your team is going to win the Super Bowl? Well, I wouldn't call it Super Bowl because I don't work for a yeah. Do you think your team's going to win the national championship, right? So for the Sounders, I don't know what it's called. What's the soccer equivalent to the Super Bowl? Does anybody know? Nobody knows, right? The Sounders Super Bowl competition. Anyway, they
World Cup.
okay. So we asked 100 from each group, and the percentage of Seahawks fans who said we were going to win the next Super Bowl came out to be 80%. And we asked the Sounder fans the same question, and we asked 100 of them, and the answer we got was 90%. So we want to see, is there any evidence to prove that Seahawks fans, less of them think their team's going to win than the Sounders, right? Basically, is P1. Oops, first it equals, and then the alternate is P1 less than P2. And hopefully we already know that these are written down in the equivalent version. Okay, I'm going to go for a 1% level. So if we get evidence to prove this, it means that Seahawks fans are definitely not as enthusiastic as Sounder fans about winning, the national championship. So we got all the start detail. We're just going to find a Z-score. P1, take away P2, huh? Over this ugly guy. And P1 hat, take away P2 hat. That's going to be 0.8, take away 0.9. Remember to put a bracket around it. And the first guy is 0.8, 0.9, oops, 0.2, sorry. 0.8, 0.2 over 100. And then it's 0.9, 0.1, also over 100. And then I start hitting buttons on calculators. We'll see if I... So it's going to be a 0.8, take away a 0.9. Can you tell this is going to be a negative number before I even finish this? Is it obvious that the top number is negative, so the whole thing is? So divided by then the square root 0.8 times 0.2 divided by 100 plus 0.9 times a 0.1 also divided by 100. And the answer I get is -2. Wow, a very surprisingly round answer. Normally you get decimals. Just a fluke of the numbers. Now, do you think a Z-score of -2 is going to be significant? Or is that a, don't know, maybe not. No, I got definite one who is saying no. That's my feeling. Let's see if it actually works out. We want to find the p-value. So it's a probability that the Z-score is less than -2, and that's called a left-tailed test because it's pointing to the left. And I then nip over to solve. And I do left-tailed. You've got to remember to hit that as well. Go over here and type in whatever the number is, in our case, -2. And the answer we got was actually pretty small, 0.023. So our p-value is 0.023, which is 2.3%. And then we ask the question, right, this is our test. Is our p-value less than the significance level? In this case, is 2.3% less than 1%? And the answer is no. So when that happens, there's not enough evidence to reject. It's not. So based on that sample, we couldn't really say for sure that there's really any significant difference between the Seahawks and the Sounders fans. Now, if you were an unscrupulous scientist or social scientist or the guy who's writing the newspaper article, you don't really want that as your answer. Can you imagine a newspaper headline? There's not really any evidence to prove there's a difference between two things. Well, there are lots of things in the world that there's not enough evidence to prove. Why do I need to read about yours? Aren't you more interested in, oh, there is evidence to prove something? So if you were unscrupulous What would be the easiest way to get a significant result without doctoring any of the data, but by just changing one thing?
Change your percentage. Or
My
your-
significance level.
Yeah,
right?
your significance.
So what would I choose? Well, wouldn't I choose maybe 5% or 10%? Because at the 5% level, won't that now be statistically significant, right? And there is a difference, right? And the Seahawks aren't as optimistic of winning as the Sounders are. 10% would do the same job. Since you are not there at the start of this process, couldn't that easily be done without you even knowing that it was done? Imagine a social scientist might have came up with this result and said, "No, I don't like that. That's nothing, not enough evidence. Oh, I'll just change my alpha to 5%. Now I can publish my paper. Or I'll change it to 10% and publish my paper." That's not good science, is it? Not a good way of doing it. If you're really, really unscrupulous, don't you have 10 different samples? You do it 10 different times until you get the answer that you want, and you only publish that one. Now, you could probably get away with that if it was a newspaper article about sports fans. I mean, who's going to lose sleep over that if you tell a pork pie, right? I would be very worried if that was done in an important situation, like trying to prove to me that a new pharmaceutical is better than an old pharmaceutical, right? That I would be really worried about. But if any, the FDA are very good at making sure that doesn't happen. Can you imagine what the fine would look like if a pharmaceutical company deliberately doctored their data in such a way to give them the results? In other words, they didn't do one clinical trial, they did 10 different clinical trials, but they only showed the FDA one, the one that worked, right? The one that said their guy's better than the old guy. And the other 9 they kept to themselves. Can you imagine what that company would be in? Well, they'd probably put somebody in jail, and if they didn't, they should, right? So I'm pretty comfortable that in the pharmaceutical industry, at least, that's not likely to happen.